Welcome back to Linear Algebra. In this video, we'll talk about the unique representation theorem, coordinates, and changing coordinates. So, the unique representation theorem. If B is a basis for vector space V consisting of vectors b1 through bn, then for each vector x in V, there exist unique scalars c1 through cn such that x is a linear combination of the scalars and vectors in the basis B. Okay, so what this means is that we can represent a vector in terms of the vectors in the basis. Okay, so the proof here, we already know that a basis will span the vector space, so we know there's going to be scalars that we can represent any vector with, but we need to prove that they're unique. So what we'll do is we're going to assume that x has another representation. So we're going to assume it has two different representations, and then we'll show that they're actually the same. So we're also going to write x as a linear combination of d1 through dn. Okay, so we need to get them to equal the same thing. So what we should do is we should work with the zero vector. And the zero vector can be written as a vector x minus a vector x. Okay, so with this, now we can take the first x as our original representation, so c1, b1, all the way up to cn, bn, and we're going to subtract the second representation. So this will be d1, b1, adding all the way up to dn, bn. Okay, so now what we can do is we can collect like terms. So we're going to get c1 minus d1 times the vector b1, and this will be consistent all the way up to cn minus dn times bn. Okay, so the next key part is that these are vectors in a basis, so they're going to be linearly independent, which means only the trivial solution exists. So this c1 minus d1, this has to equal 0. cn minus dn, they all have to equal 0. So what this means is that ci minus di is going to equal to 0 for, I'll write it like this, I greater or equal to 1, less than or equal to n, which means that ci is going to equal di for those same conditions, which mean that the two representations we have here, this x and this x, they're both the same. So there's only one way to represent each vector in terms of b1 through bn. So that's the unique representation theorem. Okay, so now that we have the unique representation theorem, we can talk about the coordinates of x relative to b. So let's say we have a vector x, and when we have the vector x relative to b, it's going to be the coefficients of the equation, so c1 through cn. Now, of course, if we take, say, a regular vector u, and we've been working with this the whole time, so let's write u as a1 e1 plus a2 e2. So let's think about this. What is this vector? Well, this vector u, a1 e1 plus a2 e2 plus a3 e3, well, these are the standard vectors in R3. So we'd also write this just as a1, a2, a3. So this is the same result. So if we take a look at this, we could actually write this as u with respect to the standard basis e. So when we take a look at this notation where x is equal to c1 b1 all the way to cn bn, and we see that the coordinate vector x relative to b is written as c1 through cn, it's really just the same thing as the vectors we've been using all along. We take a vector u in the standard basis, it's equal to a1 e1 plus a2 e2, so on and so forth, and this is really just a vector with the coefficients. So we've already been working with things like this. So let's just see how it works. Okay, so in the first example, we have b1 is equal to 3, 2, and b2 is equal to negative 4, 1. We want the vector x relative to b, and that's equal to negative 2, 5. We want to find our original x. Okay, so let's think about this. X is just going to be equal to, I guess we'll use the same numbers. So c1 b1 plus c2 b2. Well, we know all of these things. Our c1 and c2 are going to come from the vector x relative to b. So that's going to be negative 2 times b1 plus 5 times b2. b1 is equal to the vector 3, 2. b2 is equal to the vector negative 4 and 1. So our vector x is going to be negative 2 times 3, 2. So this will be negative 6 and negative 4. And then we're going to add 5 times the second vector. This is negative 20, and this will be plus 5. So our vector x is actually going to be the vector negative 26 and 1 in, so relative to b, it was negative 2, 5, but in R2, we would write this as negative 26, 1. So if we draw the R2 plane right here, this is really a vector that looks like this. So it looks the same in R2, and it looks the same in the basis b, but the basis b, so negative 2, 5, so for instance, let's take a look. We have 3 and 2, so some of the vectors, the basis is going like this, and we have negative 4, 1, and some of them are going like this. So instead of the standard cross we have a basis that looks like the purple here, and in that purple it's just represented as negative 2 in the b1 direction and 5 in the b2 direction. So you could visually draw this if you needed to. Okay, next example, we have x, we have b1 and b2, but what we don't have is x relative to b. So let's just write this the same as we did before. So we have x is equal to c1b1 plus c2b2. So this is going to look like 8, 10 is equal to c1 times 4, 2 plus c2 times negative 2, 2. Okay, so what are we looking for? C1 and C2. We know how to do this. We just need to solve an augmented matrix. So let's augment this. 4, 2, negative 2, 2, and 8, 10. What we're going to do is we're going to divide everything by 2 right away, because that will make things much simpler. So this will be 2, negative 1, 4, and this will be 1, 1, 5. Okay, so first thing we'll do is we'll take the first row, and let's subtract 2 of the second row from it. So 2 minus 2 is 0, negative 1 minus 2 is negative 3, 4 minus 10 is negative 6, and we're left with 1, 1, 5. Okay, we can basically solve this now. So negative 3c2 will equal negative 6, so this means that c2 is going to equal 2. And the second row states that c1 plus c2 is equal to 5, so c1 must be equal to 3. Therefore, our vector x relative to b is the vector 3, 2. Okay, so in R2 it's going to look like 8, 10, but in our basis it's going to look like 3, 2. They're both going to be the same direction and magnitude if we think of it like that. So if we start at the origin, the shape of the arrow and the direction of the arrow and the length of the arrow will be the same, but the way in which you get to that point based on the way the space is laid out will be different. Okay, so we have the coefficients xb. So we should probably just call this b1, b2 through bn something. So this is the change of coordinates matrix. And this is exactly what we've been doing so far, but we're just giving that matrix a notation. So we're giving it pb. So this is the change of coordinates. Now, another type of notation, we could write this as the standard basis going to be in some situations, but we'll just usually leave this out, so this will just look like the change of coordinates to b. So this is the change of coordinates basis. So we can write a vector x as the change of coordinates matrix times the vector x relative to b. And because of what we've learned earlier about linear transformations, we know that we can just take the inverse here. So the the vector relative to b is just equal to the inverse of the change of coordinates basis times x. So again, if we have something like e to b here, then the inverse of this, we could always just write this as p from b 2e. So these are two ways we can write these things. But we'll cover this notation and changing from basis to basis a little bit later. Okay, so let's find the change of coordinates basis, the change of coordinates matrix for this basis. Well, the definition is just the matrix containing b1 all the way up to bn. There's only two vectors here, so this is the matrix containing b1 and b2, and very straightforward, 1, -3, 2, -5. Of course, we could also call it 2, -5, 1, -3 if we switch the order of b1 and b2, but just to be specific, we would call this first one b1 and the second one b2. Okay, so that's it for change of coordinates. In the next video, we'll go into a little bit more detail, but for now, if you have any questions, please leave them in the comments below, and I'll answer them the best that I can.